Hello, everyone. So last time we used the first moment method to derive some results. Now today we want to use second moment method to derive results about graph theory. And I will tell you in particular what will be our goal, and we will use second method to derive which type of result. So basically today, we will use second moment method. So one of our goals here, let me tell you our goal. The goal is to prove existence of a triangle in G, N, and P, the random graph with n vertices and the edge probability P for small enough, for large enough P and non-existence of a triangle in G, N, and P for small enough P. Well, intuitively, please remember that G of N and P means random graph with n vertices where each edge appears with probability P and would not appear with probability 1 minus P. Now, if P is small compared to N, so when I say small P, we will see that, we derive formulas or expressions for P in terms of N. So when I say small enough P, I mean small in terms of N. In particular, we will see that actually the function, the explicit expression will be 1 over N. So if P is almost in the order of 1 over N or smaller, then, not enough edges would appear and a triangle would not exist, almost surely, as we will see. But if P is in the order of 1 over N, bigger than 1 over N, then, edges would appear enough as in a way that we can say that a triangle exists almost surely again. So this is what we want to do today. So let me start with some preliminaries, because we said we're going to use second moment method. So second moment in probability means expected value of x squared. Now that is of course related to variance and also Chebyshev inequality. So I'm going to provide some brief preliminaries in this regard, and also I will give a quick review about small o, big O notation, theta notation. So that's because we are going to use that today as well, and then we will get into the formal results. Okay, so let's start with some preliminaries from probability theory. So second moment of a random variable x is defined as expected value x squared. The variance of a random variable x is defined as, so variance x, the notation is expected value of x minus mu the whole squared, where mu is equal to expected value of x, and it can be shown that variance x is equal to expected value of x squared minus expected value of x squared. So these are very basic results in probability theory. I'm sure you know about them. Okay, so this is very straightforward in the case that you have one random variable, and also Chebyshev inequality is a very standard inequality in this topic. Chebyshev's inequality. Let x be a random variable with mean expected value of x equals mu and variance x equals sigma squared. Then we can say that probability that absolute value x minus mu is bigger than equal to, let's say, t sigma is less than or equal to 1 over t squared. Okay, so what does this inequality imply? Basically, it implies that, first of all, please note that, the distribution of x is not important here and not relevant. So any distribution that x has, this inequality holds. So, and basically it says that the probability that x is far from its mean is small. This is a very intuitive description of this inequality. Because absolute value x minus mu, well, you know that absolute value a minus b measures the distance between two numbers a and b. So absolute value x minus mu means the distance between x and the average mu. The probability that the distance between x and mu is bigger than t sigma is less than 1 over t squared. So, for example, if t is 5, the probability that the distance between x and mu is bigger than 5 sigma is less than 1 over 25. So the probability that x is far from mu, so what do I mean by far? Far compared to sigma. So for example, the probability that x and mu are far from each other by distance at least 5 sigma is less than 1 over 25. Or the probability, let's say if t is 10, the probability that x and mu are far from each other by at least 10 sigma is less than 1 over 100, means 0.01. So this makes sense, right? X is expected to be not very far from its mean, at least not with high probability. So this is basically what Chebyshev's inequality says. So yeah, this is standard inequality in probability, and of course, you can find the proof in any standard textbook. Okay, so this is a situation for one random variable. Now, the things would get more interesting if we have more than one random variable. So for more than one, for the case where we have more than one random variable, let's start with two random variables. Let's say if I have two random variables, x and y. So say let x and y be two random variables we call X and Y independent if, so when do we say that two random variables are independent from each other? So we would call two random variables independent if capital F, the joint CDF, cumulative distribution function, capital F X and Y is equal to capital F X of X times capital F Y of Y. I remember when I was undergraduate student, I was confused actually, because when you hear about independence, normally we would think of, probability A intersection B equals probability A times probability B, right? But that is the definition of independence of two events. Here, this one is definition of independence of two random variables. Okay, so two random variables, we would call them independent if capital F of X and Y is equal to capital Fx of X times Fy of Y. Now, these capital F's are CDF, or cumulative distribution function. So let me remind you, recall that capital Fx of X means what? The CDF of random variable X means probability that X is less than or equal to X. Or let's say capital Fy of Y, it means probability that Y is less than or equal to Y. And capital F of X and Y, the joint CDF, so this is called the joint CDF, is probability that X is less than or equal to X and Y is less than or equal to Y. Now, this note X and Y, or if you say in the case of discrete random variables X and Y are independent if and only if small p of X and Y. Well, this definition that I gave you holds for both continuous and discrete random variables. So it's a universal definition. So that's why I chose this one as a definition. If you look at different textbooks, sometimes they give this one as a theorem, for example. But this one I gave as definition because it holds for both continuous and discrete random variables. Now, if X and Y are independent, one way to check whether they're so if X and Y are discrete, one way to check they're independent or no is by looking at their PMF, probability mass function. So if P of X and Y, the joint PMF, is equal to Px of X times Py of Y, and for all X and Y. Of course, this one also must be true for all X and Y, just to emphasize, let me say. Okay, so if this is true for all X and Y, then X and Y, capital X and capital Y are independent random variable. Again, let me remind you that Px of X is equal to probability that X is equal to X, Py of Y. So these are called PMF, or probability mass functions. This is probability that capital Y is equal to Y. And P of X and Y is equal to probability that X is equal to X and Y is equal to Y. And for continuous case, if x and y are continuous random variables, then x and y are independent if a small f of x and y is equal to fx of x times fy of y. This time, these are basically PDFs, probability density functions. Where fxx, fyy, f, again, this one should be true for all x and y, of course. fxy, y are PDFs of x and y and joint PDF. So the third one is called joint PDF of x and y respectively. Okay, now let me give you a relevant example, an example that is very much related to our course and in particular what we want to do today. So for example, let's say consider G of n and p. Okay, so again, I remind you one more time, G of n and p means the random graph with n vertices and edge probability p. Or let me give you a specific one, let's say 10 and 1/3, for example. Just work with specific numbers. With the set of vertices, let's say capital V equals V1 to V10. And let capital X be the indicator random variable for the event A of having a triangle with vertices V1, V2, V3. Similarly, let Y be the indicator random variable for the event B of having a triangle with vertices V4, V5, V6. Show that X and Y are independent. Okay, so please remember that whenever we have an event, we can consider an indicator random variable corresponding to that event. How is the indicator random variable defined beside last times, right? That indicator random variable, let's say capital X of S, is either 0 or 1. When is it 0? When is it 1? If X of X, S would be 0, let's say if X is the indicator random variable for event A, X of S is 0 if S does not belong to A, and it's 1 if S belongs to A. So output of a indicator random variable is always either 0 or 1. And each indicator random variable always corresponds to an event. It would be 0, the output is 0 if the element does not belong to the event. It would be 1 if the element belongs to the event. Okay, so we have two events A and B and their corresponding random variables, capital X and capital Y. Now, these events have a feature that, they are basically corresponding to having a triangle with vertices. Both of them correspond to having a triangle. The first one with vertices V1, V2, V3, and second one with vertices V4, V5, V6. So the vertices of these triangles are disjoint. And that's why, they are going to be independent. So imagine I have a random graph with 10 vertices. So I want to know, I'm interested in the event where I have a triangle in the first 3 vertices, and another event where I'm interested in having a triangle in the 4th, 5th, and 6th vertices. So these, intuitively, it makes sense that these are independent, because the fact that I have a triangle in the first 3 vertices would not have any impact on the event where I have a triangle with vertices 4, 5, 6, because there's no common vertex between these two triangles. So intuitively, it makes sense that these are independent. Now let's see how we can prove it using the definition or equivalent definitions or theorems. So we provided the original definition using CDFs, and then we said for discrete random variables, which is the case here, we can look at their PMFs. If joint PMF small p of x and y is equal to small p of x times small p of y, then x and y would be independent. So let's look at that. So we want to show that small p of x and y, the joint one, is equal to px of x times py of y. Okay, so now this has to be true for every x and y. Now, what are the small x and small y? The possible outputs of capital X and capital Y are either 0 or 1. So first I can check it for 0. So let's say small p of 0 and 0. So what does this mean? So this means probability that capital X is equal to 0 and capital Y is equal to 0. Okay, now x equals 0. We want to find probability that x equals 0 and y equals 0. Now, when can I say x is equal to 0? Well, x is a random variable, and if I consider an element of a sample space, which is one of the possible outcomes of the random graphs, that I have, when can I, let's say if I pick one element of sample space, when can I say that for that element, capital X is equal to 0? If that element does not belong to A. And what is A? A is the event where I have a triangle between vertices 1, 2, 3. So X equals 0 means not having a triangle between vertices with vertices V1, V2, V3. Okay, so let me repeat one more time that an element of sample space if I consider an element of sample space, x of that element is 0 if there is no triangle with vertices 1, 2, 3. And y would be 0 for that element if there is no triangle with vertices 4, 5, 6. Okay, so what is the probability that x equals 0 and y equals 0? So that means probability that having no triangle with vertices v1, v2, v3 and having no triangle with vertices v4, v5, v6. Okay, so in terms of original events A and B, I can say that this is P of A complement intersection B complement. A was the event that I would have a triangle with vertices v1, v2, v3, and B for having a triangle with vertices v4, v5, v6. Now I want to have no triangle with v1, v2, v3, and no triangle with v4, v5, v6. Now this one I can write it as using the features, properties of probability. I can write this one as 1 minus P of A union B, right? Because of course A union B is the complement of A complement intersection B complement by De Morgan's law. And then this one I can write 1 minus P of A union B. You know the formula, right? It's P of A plus P of B minus P of A intersection B. So then this is 1 minus P of A minus P of B plus P of A intersection B. Now what is P of A? Well, A is the event that I would have a triangle with vertices V1, V2, V3. Now, that means that I would have a triangle if all these three edges would appear and each one would appear with probability P and they're independent of each other. So P of A is P times P times P, which is P cubed. Similarly, for the event B, which is the event for having a triangle with vertices V4, V5, V6. Again, B would happen if all these three edges would appear, and that would happen with probability P cubed, plus P of A intersection B. So A intersection B means A and B, both of them happen. So when can I say I would have a triangle between V1, V2, V3, and another triangle with vertices V4, V5, V6? So this would happen if and only if three edges would appear here and three edges would appear here. So 6 edges, each of them, again, independent of each other. And that would happen with probability P to power 6. So this is 1 minus 2P cubed plus P to power 6. Now I can write this as 1 minus P cubed times 1 minus P cubed, right? Using the identity A minus P the whole squared. I can write this as 1 minus P cubed times 1 minus P cubed, which is probability, basically probability that capital X is 0 times probability that capital Y is 0, right? Well, capital X equals 0 means having no triangle between vertices V1, V2, V3, which is 1 minus probability of having a triangle with vertices V1, V2, V3. And that means 1 minus P cubed. Similarly, P of Y equals 0 means 1 minus P cubed. And this is Px of 0 times Py of 0. So that means we showed that P of 0, 0, the joint PMF is Px of 0 times Py of 0. Okay, similarly, check that P of x and y is equal to Px of x times Py of y for x and y equals. So for 0 and 0, we checked it. So 0 and 1, or 1 and 0, or 1 and 1, which are other possibilities for the pair x and y. You can check that this equality holds. And therefore, this means that x and y are independent random variables. Okay. Okay, now let's look at the definition of a covariance between two random variables. So let x and y be random variables with means mu x equals e of x and mu y equals e of y. Then covariance x and y is defined as follows. So covariance x and y is defined as expected value of x minus mu x times y minus mu y, which can be written as expected value xy minus expected value x times expected value y. So it's a simple exercise to show that the first expression is same as expected value xy minus e of x times e of y. Okay, so also correlation or correlation factor of x and y denoted by rho xy is defined as, so rho xy is same as covariance, but it's normalized version. So this is defined as covariance x and y divided by sigma x times sigma y, where sigma x is square root of variance x, the standard deviation, right? So square root of variance, and sigma y is square root of variance y. Okay, so it can be shown, note, can be shown that rho xy, the covariance factor, is always between -1 to 1. So covariance itself can be any number. So please note that variance is always positive, same as standard deviation, or non-negative at least, but covariance can be positive or negative and can take any number from -infinity to infinity. But if you normalize covariance, which is going to be called correlation, then that case you're going to get a number between -1 to 1. Okay, so next definition is x and y are called uncorrelated if covariance x and y is equal to 0, which is same as rho x and y equals 0. So if covariance is 0, we are going to call X and Y uncorrelated. Now, an important question in probability theory is, can we say that uncorrelated and independent, are they same, or are they same concepts? Uncorrelated random variables and independent random variables. The answer is no. Any two independent random variables for sure are going to be uncorrelated, but not conversely. So it's possible that two random variables are uncorrelated, covariance is 0, but they are not independent. I'm going to give you the example for that. So theorem is that if X and Y are independent, then E of xy is equal to E of x times E of y, and hence covariance xy is equal to 0. Right? Remember, covariance x and y is expected value xy minus expected value x times expected value y. So if E of xy is equal to E of x times E of y, covariance will be 0, which is the case if x and y are independent. Okay, but the remark is, it is possible that x and y are uncorrelated but not independent. So what is the example of such a case? Let x be a random variable with standard normal distribution, so n 0 and 1, and y equals x squared. Then x and y are not independent. Well, intuitively, it's obvious that x and y are not independent because we are saying that y is equal to x squared. How come x and y can become independent? I'm saying that one of them is the other one squared. Of course, they are dependent. But you can check this. If you want to do this formally, you have to do it with the formal definition or equivalent versions of independence of two random variables for the continuous case, because standard normal means x is continuous. You can look at, for example, their PDFs or CDFs and show that the joint PDF is not product of individual PDFs, or joint CDF is not product of individual CDFs. So you can check this. But note that covariance x and y in this case would be 0. Why? So let's see, covariance x and y is equal to expected value xy minus expected value x times expected value y. Well, y is x squared. So this is expected value x cubed minus expected value x times expected value x squared. Now, x is standard normal. So standard normal means it has mean 0, variance 1. So E of x is 0. E of x cubed will be also 0. So this is equal to E of x cubed. And this is also 0 because expected value x cubed. How would you find expected value x cubed? We just need to integrate x cubed times PDF of standard normal, which is 1 over root 2 pi e to power minus x squared over 2 dx from minus infinity to infinity. Now this is an odd function, right? An integral of odd function from minus infinity to infinity assuming the convergence, which is the case here, is 0. Okay. Okay, another result that we need for this topic is the following lemma. So let x1, x2 be a sequence of random variables and assume that limit variance xn divided by expected value xn the whole squared as n goes to infinity is equal to 0, then limit p of xn bigger than 0 as n goes to infinity is equal to 1. And this means that xn bigger than 0 asymptotically almost surely, or abbreviated by AAS. So almost surely is a term used in probability theory that is used when we say an event happens almost surely. It means it happens with probability 1 and it would not happen with probability 0. So this is the meaning of almost surely. But now asymptotically almost surely, well, you know that when in asymptotic analysis, we study behavior of, a function or a sequence of random variables, ultimate behavior of basically some objects as n goes to infinity if they're a function of n. But basically in asymptotic analysis, we look at the ultimate behavior of objects of study. Now, in this case, it's sequence of random variables. So when we say asymptotic behavior of this sequence of random variables, so that's what we want to study. Now, asymptotically almost surely, so when we say xn or an event or a property holds asymptotically almost surely means the limit of the probabilities of that event converge to 1. So the probability of sequence of events converge to 1. In that case, we would say that that event happens almost asymptotically almost surely. Okay, so basically we want to say that if you have a sequence of random variables and this property holds, then ultimately we can say that the xn will be bigger than 0 almost surely. So this is important because remember that our common technique in this course is to show existence of a specific structure by showing that the probability of existence of such a structure is non-zero. Okay, so we would say that probability that xn bigger than 0 is equal to 1. So remember I told you that our goal in this topic using second method is to show that if you consider random graphs g of n and p, if p is large enough compared to n, specifically bigger than 1 over n, order 1 over n, then we can say that almost surely the random graph g of n and p contains a triangle in it. So you can guess that, in our context, xn would count the number of triangles. So probability that the number of triangles bigger than 0 means probability that at least one triangle exists in our graph converges to 1. So that means almost surely our graph g of n and p would contain a triangle. Okay, so this is what we will go. Of course, we'll get to the details later, but now let's prove this lemma first. Proof. So basically the proof is a simple application of Chebyshev inequality. So by Chebyshev's inequality, what can I say? We can say that probability that absolute value xn minus e of xn bigger than e of xn is less than equal to 1 over e of xn over sigma the whole squared. See, remember what was the Chebyshev inequality? P of absolute value x minus mu bigger than equal to, well, I said T sigma, but I can call T sigma as, let's say, S, and then this will be less than equal to 1 over S squared over sigma squared, which is sigma squared over S squared. Remember the original version of Chebyshev inequality, we said probability absolute value x minus mu bigger than T sigma less than 1 over T squared. Now if I call T sigma as S, T sigma as S, then 1 over T squared would become, T would become S over sigma. So it would become 1 over S squared over sigma squared, which is sigma squared over S squared. Okay, so we can say that probability that absolute value x minus e of xn bigger than equal to e of xn less than equal to sigma squared over e of xn the whole squared, which is variance xn. So by sigma squared here, I mean variance of xn. So variance xn over e of xn squared. Okay, so what can I say then? So I can say that P of x minus e of xn bigger than equal to e of xn, or x minus e of xn less than equal to minus e of xn, is less than equal to variance xn over e of xn the whole squared. So this means P of x bigger than equal to 2 e of xn, or x less than equal to 0, less than equal to variance xn over e of xn the whole squared. And this means P of x less than equal to 0 is less than equal to variance, so xn, these are also xn. Yeah, here also xn, this one also xn, 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 variance xn divided by e of xn the whole square, right? So because of course P of xn less than equal to 0 is itself less than, so this term here is less than equal to this term, right? P of A union B compared to P of A. P of A is of course less than equal to this one, and this one is less than this term. So I can say that this one, which is less than this one, of course, will be also less than this term. Thus, by letting n go to infinity, what can I say? I can say that limit p of xn less than equal to 0 as n goes to infinity will be 0, right? Because the right hand side as n goes to infinity goes to 0. So p of xn, limit p of xn will be less than equal to 0, and probability, of course, cannot be negative. So this probability will be 0. And this means probability limit p of xn bigger than 0 as n goes to infinity is equal to 1. If p of xn less than equal to 0 is 0 as n goes to infinity, means the complement, which is p of xn bigger than 0, has to be 1 as n goes to infinity. Okay, another result that we need for this topic is basically variance for variance of sum of few random variables. So basically we need a formula for variance of sum of few random variables. So let me also mention that as a lemma. We first state it for two random variables. Let x and y be two random variables. Then variance x plus y is equal to variance x plus variance y plus two covariance x and y. This one is easy to prove, variance x plus y. If I start from the left hand side, this is expected value of x plus y the whole x plus y the whole squared minus expected value x plus y the whole squared. And then this one is expected value x squared plus y squared plus 2xy minus expected value x squared plus expected value y squared plus 2 times expected value x times expected value y. And then this one is expected value x squared minus expected value x squared plus expected value y squared minus expected value y squared plus 2 times expected value xy minus expected value x times expected value y. And then this one is variance x plus variance y plus 2 times covariance x and y. Okay, so this is variance of two random variables. Now a similar calculation can be done for n random variables. So more generally, if you want variance, let's say x1 all the way to xn, I can write this one as variance x1 plus all the way to variance xn plus 2 times, let me say sigma covariance xi xj I less than j. Okay, so I can also write this one as, let's say, variance x1 to variance xn plus sigma covariance xi xj if I just put I not equal to j. So if I put a sigma over just I not equal to j, then I don't need extra factor of 2, but remember that covariance x and y same as covariance y and x. So covariance xi xj same as covariance xj xi. So I can say 2 times covariance xi xj, but then I need to put the restriction I less than j or I bigger than j. Okay, now this formula has another version as well. Now look at this version. In this version, I put the restriction I less than j, and then I need extra factor 2. If I don't put that restriction, only restriction I not equal to j, then I don't need extra 2, that extra factor of 2, but still I need to add variances and then covariances. Now, what about if I don't put any restriction at all here? So this one I can write it as sigma covariance xi xj. And if I put no restriction at all, I'll just say I and j from 1 to n. Then this expression is same as this expression. Why? Well, you just need to remember that variance xi is same as covariance xi and xi. Right? So you can easily check that variance xi is covariance xi. You can easily see this by using the formula that we have for variance and covariance. Variance x is ex squared minus ex squared. Covariance xy is exy minus exey. So you can easily see, check this is true. And then, so variance x1 is covariance x1, x1, all the way to variance xn is covariance xn, xn. So I can replace these variances in terms of covariances. So I would get covariance xi, xj, and I and j from 1 to n. So if I is not equal to j, I'm going to get these terms. And if I is equal to j, I'm going to get covariance xi, xi, which is variance xi. And then I'm going to get these terms. Okay, so this formula and this formula and this formula are all equal. So I explained for you the reason, but the proof of this is similar to the one we did for 2 random variables, and you can do it as exercise. So proof exercise. Okay, so yeah, these are some preliminary stuff that we need for this topic. So I'm going to continue the rest in another video. And we are going to get into the details of the main basically results that we want to do in this topic and use second moment method. Okay, thank you and see you soon.